Hello everyone, I'm Akshay. Today I'll be presenting my paper Dual Active High Bridge Converter with Integrated Active Port Decoupling for Onboard EV Charger. Coming to motivation, we all know that electric vehicles offer benefits like low maintenance, low pollution levels, and low running cost. Owing to these benefits, significant steps have been taken to promote EVs, but their acceptance is limited due to inadequate charging infrastructure and range anxiety. One of the solutions to overcome these challenges is a fast onboard charger. However, for the fast onboard charger to be attractive in two-wheeler segment, it needs to have high power density, high efficiency, and a reliable design. Two-stage architecture is a popular choice for fast OBCs due to its time-proven design and simple control. However, a common problem associated with single-phase OBCs is a power decoupling. The power drawn from the utility grid contains two components, an average component and a second harmonic ripple power component. The average component is nothing but the power delivered to the battery, whereas second harmonic ripple power component has to be buffered in an energy storage element. A common approach to buffer this ripple power is to use a large value of DC-link capacitance, which is realized using an aluminum electrolytic capacitor. But the problem associated with the use of AEC is that the reliability of the converter is reduced. So the alternative is to go with active port decoupling. Active port decoupling circuit is basically a bidirectional converter which decouples the voltage regulation and the energy requirement. As a result, the value of capacitance required to buffer ripple power is significantly reduced. As a result, a high reliable film or ceramic capacitor can be used. But a dedicated APD circuit requires additional switches, which increase the cost of implementation and the efficiency is reduced. So the solution to this is to go with integrated active port decoupling. Here the APD is integrated with one of the stages, that is either the PFC stage or with the DC-DC stage. A lot of research has been done where the APD is integrated with PFC stage, and two such approaches has been listed over here. In the first approach, a symmetrical half-bridge APD is integrated with the PFC stage. But the problem associated with the use of APD is it requires a large value of buffer capacitance. To tackle this large value of buffer capacitance, a buck-based APD circuit is integrated with PFC. But the problem associated with this configuration is the voltage stress across the power devices increases. Moreover, integrating APD with the PFC stage requires the use of active rectifier, which increases the switch count. As a result, it is beneficial to use a high efficient PFC stage and integrate APD with the DC-DC stage. So two such approaches have been listed over here, where APD is integrated with the DC-DC stage. In the first approach, the APD is integrated using a center tap transformer. The problem associated in doing so is the transformer processes the ripple power, which makes it bulkier. In the second approach, a buck-based APD circuit is integrated with one of the bridges of dual active bridge converter. The problem associated with this thing is it uses process square wave modulation, which reduces my overall efficiency. So looking at the above mentioned disadvantages, the following topology has been proposed. Here, a high efficient totem pole PFC circuit is used in the front end, and APD is integrated with one of the bridges of dual active half bridge converter. So the advantages of doing so is I do not require any additional switches. Also, it uses a rectangular modulation, which unlike a process square wave modulation doesn't lower my efficiency. Moreover, by optimal selection of the passive components, the device stress can be minimized. From working point of view, the DC-DC converter has two major functionalities. One is to buffer the second harmonic ripple power, and other is the average power transfer. Coming to second harmonic power buffering, basically these capacitors are being used to buffer the ripple power. Among this, the top capacitor is just a high frequency filter capacitor and will not contribute much in power buffering. It is only the bottom capacitor which is contributing for the power buffering. Now, if you look at the power drawn from the utility grid, it contains two components, an average component and a ripple component. Now, for active power decoupling to be achieved, the power exchange by top capacitor plus power exchange by the bottom capacitor has to be equal to the ripple power. Moreover, the sum of these two voltages has to be equal to the DC-link voltage. So we have two equations and two unknowns, solving for which we get the expression for the voltage across the bottom capacitor. If the bottom capacitor voltage follows this fashion and the DC-link voltage is maintained constant, then the active power decoupling is achieved. From working point of view, it's actually basically a buck converter. By appropriately controlling the duty cycle of top switch, I can control the voltage across this bottom capacitor and I can achieve active power decoupling. Now going for the second major aspect, that is the average power transfer. So in this DC-DC converter, we basically have 3 degrees of freedom. The first one is the duty cycle of the primary switches. The second is duty cycle of the secondary switches, and the third is the phase shift between them. Here, the duty cycle of primary switches is used to achieve active power decoupling, and we are only left with the 2 degrees of freedom. But to minimize the circulating current, the duty cycle of secondary switches is maintained same as that of the duty cycle of primary switches, and it is only the phase shift which is controlling the average power transfer. Now let's look at the control aspect of the converter. So the blue color section over here is the controller for the controller for the second harmonic power buffering, and whereas the yellow color section is for the average power transfer. So the buck converter is controlled using a current controller, and the current references for this is generated using a ripple voltage controller and an average voltage controller. So this ripple voltage controller, nothing is exactly what it does is it extracts the ripple from the DC link voltage using a bandpass filter, and this ripple in the DC link voltage is compared with a zero reference and is passed through a proportional resonant controller to generate the respective current reference. Whereas the average controller block over here is used to maintain the average voltage across my bottom buffer capacitor to the designed value. So any changes with respect to that will generate the respective current reference and active power decoupling is achieved. Now, for the average power controller, the phase shift is generated using an open loop reference generator. Now, the phase shift required to transfer the average power is a function of the power that has to be transferred, the current battery voltage, and the duty cycle at which the APD circuit is operating. So an expression is obtained for this, and the phase shift is generated using this idealistic equation. Now, any other correction factor due to circuit non-idealities and parameter variations is generated using this traditional CCCV controller, and the respective phase shift is generated. Now, to verify this control action, a simulation has been performed. So the software that has been used is the Plex for validating the control behavior, and for efficiency point of view, LT-Spice has been used. So the converter is designed for a 3.3 kilowatt and to deliver power to a 72 volt nominal voltage battery pack with a maximum voltage going of around 84 volts. So the rated output power of the converter is like 84 volts and 40 ampere. The other passive parameters have been designed so as to minimize the device stress on my power semiconductor devices. So these are the waveforms for the waveforms at rated load. So as you can see here, the output current has the ripple has of only 2 amperes, so which corresponds to less than 5% of my full load current. And this is the DC link. As you can see, the DC link voltage is maintained almost constant to 400 volts with a ripple of around 1.9 volts. Whereas the red color one is the voltage across the buffer capacitor. As you can see, the ripple in the buffer capacitor is around 190 volts, which means it is properly being utilized. And coming to the grid current and grid voltage, as you can see, the TSD is also maintained within limits. It's around 3.54%. This green color waveform over here is nothing but the current flowing through the transformer winding. So this is basically to ensure that the device's currents are within its limits. Now, if you look at the loss breakup at the rated load, an efficiency is around 95% is expected, which is well good enough. So conclusion point of view, so in this paper, a technique for integrating APD circuit with a dual active half-bridge converter is provided. A control scheme for the proposed topology is presented, and some circuit simulation studies is carried out to verify the control aspect. And this topology achieves close to around 80% reduction in the value of buffer capacitance required. Also, it maintains a ripple in the DC link voltage below 1% and the ripple in the output current below 5%. And based on the loss model estimation, efficiency of around 95% is expected. These are the references for the existing literature survey. Thank you.